Welcome back, welcome back, welcome back. I'm Miss Lisa. This is my YouTube channel where we talk about everything I want to, science and math. And this is a video for solutions, and this is going to be part 2 of 3 because I got a phone call in the middle of that video on a phone that's not even hooked up to a plan. How did that happen? It's like a time machine or something. I don't pay for a plan on that phone, but somehow I was getting a phone call. I don't know. So anyway, talking about solutions. The solvent is what does the dissolving. The solute is what gets dissolved. And so how much is dissolved is another thing that we worry about in chemistry, and that we have rules of solubility. What can dissolve what? And we'll look at that a little bit, but once again, that's the thing that will go much more in depth with AP Chem or Chem 2 or college chemistry. But anyway, so temperature affects how well a solid can dissolve in a liquid. So with that sweet iced tea, the sugar can dissolve when it is hot, but once it's cold and they bring that little packet, it's not going to dissolve. It's just, you're going to just try to stir it real fast to get the sugar going everywhere, and then try to drink it real fast before it has time to settle to the bottom. So temperature affects how much can dissolve if you're putting a solid into a liquid. The hotter the temperature, the more that can dissolve. Now, it's the opposite of that, though, with a gas. Remember that Coca-Cola by the swimming pool? As it heated up, less gas is dissolved. The bubbles come out. The dissolved carbon dioxide, that is the bubbles in the Coca-Cola, they come out of solution and the Coke goes flat as the temperature increases. So gases dissolve in liquids better cold, and that's and under pressure. So it's gonna, so when you open that Coke, it opens, you can hear that pressure being given off. But with the solids and the liquids, the pressure doesn't really matter. Unless there's so much. We're going to talk a little bit about vapor pressure above, depending on what it is. But with the gases, it's got to be under pressure and cold. So if you ever get to go do a field trip to a bottling company and see this, it's going to be cold, it's going to be under pressure, that they are dissolving the gas. I did that field trip, and my oldest son did when he was homeschooled. But by the time the younger two came along, the Coca-Cola bottling plant around here wasn't doing trips anymore. They just sent everybody to World of Coke. Go to World of Coke and watch a big old Coke ad pay money to watch Coke ads and drink Coke from around the world. It's kind of interesting, but it's a little bit of a ripoff, I think. You're paying money to go watch a Coke ad. It's not nearly as good as going to the factory and seeing them make it how we used to. You'd get these little bitty bottles of Coke at the end. It was fun. And then when Nathan went, my kid went, they got like new flavors of Coke that they were trying to, and I think it was a Sprite, which you're going to laugh, but that they were going to introducing. All right. So have you ever seen a kid add so much sugar to their cereal that at the end it won't dissolve? Okay, so if more can dissolve in something, it is called unsaturated. But there becomes a point that at that temperature, no more can dissolve. And that is called saturated. Now, there's something called supersaturated also, which is you take it and you heat it up. You put in as much as can be dissolved at that temperature, but then you let it cool down without bumping it. You just let it sit really still, and you slowly let it cool off, and there will be more dissolved in the solution than it can dissolve at that temperature. But if you put a few grains of undissolved in there or bump it, it'll go and crystals will grow. We used to do that in my lab with some polyvinyl crystals that we would do that with. This is not it, but it is like if you ever take a water bottle and you get it right at freezing, and then you hit it and it goes and it all freezes. It's like that. Now, it's not the same because in the water bottle, it's just water. And what you're doing is you're right at freezing point. And what this is crystals growing, it coming out of solution. So that's saturated, unsaturated, supersaturated. Factors of evolving solubility is temperature and what it is. If you look in your book on page 463, you see solubility curves. It's graphs that show how much of something will dissolve at that temperature. For example, you can dissolve salt all the time. No matter what the temperature, salt's going to dissolve in water. But sugar, the water's got to be heated up to get it to dissolve. Different compounds, different solubilities. That makes sense, doesn't it? All right. Now, there's a thing called Henry's Law. That's really more of a Chem 2 thing, so don't worry about that. I'm going to go through and do a third video to show you the math. You're going to be doing the solutions in colloids lab on page 466. There's a thing called Tyndall Effect, and it's if you can tell if something is a solution or a colloid. Colloids are cloudy, so milk is a colloid, where Kool-Aid is a solution. And these terms are a little bit ambiguous. I'll tell you what the actual official definition of solution is and how it is used in practicality and chemistry are two different things. The real practicality is if something is called a solution, it is clear. It can be colored like Kool-Aid, but it is clear. Where colloids are cloudy, and you can remember that because colloids and cloudy both start with the letter C. So on this lab, what you do is if you can see like what looks like a sunbeam in the solution, then it's a colloid. If you can't, if the light is scattered, it's a solution. So what you're going to do is maybe add milk or cornstarch and shine a flashlight through it. If you have a laser, it would be even better. If you've got like a little pin laser thing, shine it through and see if you can see the beam. So it's like when you're at your house and it's late afternoon and the sun comes through the window and you thought your house was completely clean, but you can see all this dust in the beam. That beam going through your beaker, or if you could just use a glass, jelly jar, whatever you got, a plastic cup, clear plastic cup, that Tyndall, that effect is named after Tyndall. And I always thought, I could have figured that out. There are things I couldn't have figured out. E equals MC squared, never in a billion years. Barely understand parts of Einstein's theory of relativity now. I just can't wrap my brain about parts of it. But Tyndall Effect, I'm like, man, I messed out. I should have discovered that. It could have been the Blackburn effect. All right. Now, we have to be able to have different concentrations. We can't just say it's concentrated or dilute. We have to know exactly how much. And a lot of what I do as a high school chemistry teacher is I make solutions. I go back into my stock room, I get the chemicals, I make solutions of certain concentrations. So we have to have a way of telling how concentrated it is. And we actually have a couple. The one I usually use as a high school chemistry teacher is called molarity. And it is symbolized by a big M. That's what my dad used to call my brother when he was little, because he was Michael. He'd call him Big M. I don't know. But it's the moles of solute divided by liters of solution. And it's written in square brackets. So like I just made some 3 molar sodium hydroxide for my public school kids for this fun little lab we did where we zinc plated and brass plated pennies. And we put it, I would write it, I had my flask. I don't always want to have labeled things in the lab. I don't want to, like if something happened to me, I don't want someone to go, oh, this is a mystery chemical. What is it? I want someone to know. And so I labeled it 3 in those square brackets, 3M. And any scientist would know this is 3 molar sodium, and I wrote on NaOH, sodium hydroxide. So that's one way, and that's what I use as a chemistry teacher. But in industry, they're not making just one little beaker. They're making tons and tons and tons to sell. So they don't get out a, graduated cylinder to measure what they're making. They do it by weight. So instead of doing molarity, they do molality, which is kilograms. It's the moles of, molality is moles. Molarity is moles per liter. Molality is kilograms. It's all weighed out. So that's the difference there. Does your book talk about molality? Because I might have been teaching you something that's not even in your book. Oh well, there's another one that you would use in industry, molality, and I don't think it's in here, but you use kilograms instead. All right, so there's some math I'm going to teach you on the next one. Dilutions is where you put more water, put more solvent in it, and we're going to talk about how you do that. Percent solutions, sometimes you do percents of volumes instead of doing moles. Remember, moles is Avogadro's number of anything, and it's 1 mole per liter is a 1 molar solution. 2 moles per liter would be 2 molar. I made a 3 molar solution of sodium hydroxide, 3 moles per liter. I actually made a liter, so usually I don't. I usually have to cross multiply solve for X with a ratio. Let's see. Colligative properties. That's fun to say. What that is there are certain properties that it matters how many particles are in it. It changes the properties of the thing. You sort of know about this. It is freezing point depression and boiling point elevation. That if it's gonna ice outside, they put salt on the roads. They're adding more particles, so that is a colligative property. Colligative properties depend on the number of particles. More particles, it makes the freezing point go down, so the roads won't freeze and people don't go slip sliding around. Same thing with boiling. If you add salt to your spaghetti water before you put your spaghetti in, you have raised the boiling point. It's going to boil at a higher temperature. Your spaghetti is going to cook a little faster. Plus, the salt goes into the spaghetti and it's going to taste a little better too. So those are colligative properties. Your book has some good pictures that you can look to help understand that better. They do have molality, moles of solute over, it says 1,000 grams of solvent. That would only be water. It's kilograms of solvent. But that doesn't make sense. Just read it and just know that that's not really all that important unless you are a chem major and then you work in industry. And by then you'll be really good at it because you'll be a chem major. So, let's see. We're not going to do much with that. And that's it for this chapter. So like, share, subscribe. Science is great. Come back and watch part 3. I'm going to show you the math up closer. All right? See you soon.